Hello and welcome. This video will continue our discussion on problems on types of relations. Like so, here we have a set T. We have a set T. It is a set of all triangles in the Euclidean plane. So it has all the triangles like isosceles triangles, equilateral triangle, and general triangles, etc. So, but in the relation we are taking only triangles which are congruent to each other, like A is congruent to B. So here A comma B is a relation where A is congruent to B and A comma B belongs to D. So we have to check for the properties, like we check for reflexive property. So if a triangle, we have a triangle like this, let's say this triangle is A, and if you reproduce the same triangle A, so A is congruent to this triangle A. So a triangle is congruent to itself. So every triangle is congruent to itself. So all the congruent triangles can be matched to itself. Like if I have triangle A which is congruent to A, I have triangle B, it is congruent to itself, C is congruent to itself, and so on. So this is reflexive. We'll check for symmetric. So if a triangle A, if I have a triangle A which is congruent to B, then B is also congruent to A. Congruency means they are identical triangles. So if I have two triangles like this, they are identical. It means angles are same, corresponding angles are same, and the sides are equal as well. Say if I have, let's say if I have triangles A, B, C and D, E, F. So if I want to say ABC, triangle ABC is congruent to triangle DEF, then all the angles are same. Angle A is equal to D, angle B angle A, angle B is equal to angle E, angle C is equal to angle F, and all the sides are corresponding sides are equal. AB is equal to DE, BC is equal to EF, and AC is equal to DF. So it means they are identical. So if A is identical to B, B is also identical to A. So it is symmetric. Next, for transitivity, if A is identical to B and B is identical to C, then A must be identical to C, because all these triangles will look same. So this is an equivalence relation. Let's move on to the next problem. So we have a non-empty set which consists of number of children. Let's say we have children A, B, C, D, and so on. So children may be males, females, males, and it's a mix of both the genders. Now we have to check the relation. The relation is given like this. We have to pair A comma B, where A is brother of B. A is brother of B. A comma B is a member of set. So is it reflexive or not? Let's check for reflexive property. Reflexive. So if I take the same element twice, let's say we have A and A. So a person cannot be brother to himself. A person cannot be brother to himself. So himself. So this is not reflexive, clearly not reflexive. Next, for symmetric, if A is brother of B, if A is brother of B, belong to R, or is B a brother of A? So this will be true only if both AB are males. Let's say if A is male and B is female, then B cannot be brother of A. B cannot be brother of A. So this is clearly not symmetric. Not symmetric. Let's check for transitivity. Check for transitivity. Let's say we have A is brother of B. A is brother of B. So if B comma C has to exist, then B is if B is brother of C, B is brother of C, then this should be a male. Then this should be a male. So if B is male, then A also should be male because A is brother of B. If B comma C has to exist, then B has to be male. B has to be male. So this can be both female or male. This doesn't matter. So if this is the case, then whether A comma C is a member of R or not, it is a member of R because A is brother of B, B is brother of C, so A has to be brother of C, irrespective of gender of C. Even if C is female or C is male, A should be brother of C. So it is clearly transitive. It is transitive. So the relation is transitive but not symmetric. Let's move on to the next problem. So here we have set is complete real number 0, 1, root 2, 2.5 and so on. Negative numbers, negative fractions, negative irrational numbers and so on. All this belongs to real numbers. So we have the relation. We have to take two numbers a comma b such that modulus of a minus b is less than or equal to 1. For example, relations you can write as if I say, let's say 0 comma 1, because 0 minus 1 is less than or equal to 1. 1 comma 0 I can write, and we can write 5 comma 6 because 5 minus 6 is minus 1, modulus of minus 1 is plus 1, 1 is that is less than or equal to 1. I can take 6 comma 6, which is 6 comma 6 is 6 minus 6 is 0, which is less than or equal to 1. There are so many things like this. We need to check for the properties. Let us check for reflexive property first. So can every element be included? Can every element of this set, can it be paired to itself? So that is a question. Let us take if I take 5, if I pair 5 with 5, so it is 5 minus 5, which is 0, which is less than 1. Modulus of this is less than 1. So 5 comma 5 is a member of R. So if you take, let's say, root 2, I'll take minus root 2. So minus root 2, if I combine with minus root 2, what happens? So minus root 2 is minus root 2 minus of minus root 2, which is modulus of minus root 2 plus root 2, which is 0, and this is clearly less than or equal to 1. So what I'm trying to say is, if I take a minus b under mod, if I pair every element with itself, so it becomes a comma a, is it a member of R? So if I do a comma a, means a minus a, modulus of a minus a is always, modulus of 0, it is always less than or equal to 1. So we in this relation we have every element paired to itself. So it is clearly reflexive. It is reflexive. Let us check for symmetric property. For symmetric property, if I take, let's say, if I take 5 comma 6, 5 comma 6 is 5 comma 6, modulus of 5 minus 6 is actually modulus of minus 1, which is plus 1, and this is clearly less than or equal to 1. So if I make 6 comma 5, 6 comma 5 is 6 minus 5, 6 minus 5 is 1, mod of 1 is 1, so this is less than or equal to 1. So if 5 comma 6 is there, is a member of R, then 6 comma 5 has to be a member of R. Like if I have A comma B, then if A minus B is less than or equal to 1, then if I interchange this B comma A, this becomes B minus A. This I'll write it as minus of A minus B. So modulus of minus is A minus B itself. So here in the previous case, modulus of A minus B is less than 1. So this is less than or equal to 1. So just by interchanging, the modulus will not give you any different result. Hence for every A comma B in the relation R, B comma A should be present. Right? If I take, let's say if I take 5 and 3, then 5 minus 3 is 2. 2 is not less than or equal to 1. So 5 minus 3 itself is not a member of R. So if you take any element, any ordered pair which satisfies this condition, which is this condition, then B minus A will satisfy the same condition. So I can say this relation is symmetric. This relation is symmetric. Let us check for transitivity. For transitive, so what I do is I take 3 elements A, B, and C. I'll take 5 and 6 here, 6 and 7 here. So A comma B is 5 comma 6. 5 comma 6 clearly is a member of R because 5 minus 6 is minus 1. Minus 1 mod is plus 1, which is less than or equal to 1. So this is a member of R. If I take 6 comma 7 also, this is a member of R because 6 minus 7 is minus 1. Modulus of minus 1 is 1, which is less than or equal to 1. So now I have to check whether A comma C is a member of R or not. A is 5, C is 7. So 5 minus 7 is 2. Modulus of 5 minus 7 is plus 2, which is not less than or equal to 1. So this is not a member of R. So this is not transitive. So the relation is only reflexive and symmetric. It is both reflexive and symmetric, not transitive. Let's move on to the next problem. Okay, so this is an interesting problem. So we have to check whether this relation, this division, where the division as a condition